Hello, my name is Renaraman Saho, and we'll be discussing about the physics of materials. The last week, it was mostly on the how did we measure the electrical conductivity, both AC and DC, and why it is that we want to focus so much on the conductivity of a material. It is because it is the first thing is that electronics are ubiquitous. Everywhere we see electronics, and one of the most important thing is that given the available material that we have at our disposal, conductivity values span a very wide range of magnitude, over 27 orders of magnitude, and it is like no other properties which have this wide range. And another thing is, it is a scientific interest to understand what it is. Most of the conducting spaces are usually electrons and holes, particularly used in the semiconductor industry, and in power sources like in phones, in computer batteries and all. You might have heard about lithium-ion batteries. So ionic spaces are used as the electrolytes in them. Okay, so these are the mostly the conducting spaces. So yeah, in a electrochemical power source. So this is a schematic diagram of it. Particularly in the electrolyte, the electronic conductivity is low and ionic conductivity is really very high. That doesn't mean that electronic conductivity is not there in the electrolyte. It is there but low. Another device example that was given in the lecture was this transistor, where you have this emitter, base, and collector, and the major charge carriers are holes and electrons in them. How do we measure this conductivity? One is this two probe method. In two probe method, why it is called two probe method? Because this particular circuit is connected to the sample at 2 points, and there is this is the a disadvantage of two probe method. You can say these are the two contacts, one and two, where the probes are in contact with the sample, and if you look analyze the potential drop, then there would be a potential drop on the wire, the connecting wire, potential drop across the contact, and potential drop across the sample, the second contact, and the wire connecting to it. This is what we actually measure in two probe measurement. But what we actually want is
That,
this.
that you show negligible, right? That value of drop is negligible, right? Normally,
Which drop is negligible?
the potential drop in the wire or the
In the
connecting
wires are
wire will
negligible,
be
yeah, but still it is there. But it is negligible, yeah, that's uh, true. Yeah. Now, so this is a four probe method where we're connecting at four places. And what is happening is, uh, one of the advantage here is, see, this voltage, it can directly, so it actually sees the potential from here to here, and the potential, some current can be pumped in from here as well, and it will, uh, a very little amount of current will go in here and some current will go in here. But here, what we in four probe method, the current that goes in, well, a little, it is really very less, but it goes on, whatever goes on, it goes on through this sample only. So the potential drop that we will see is actually from the sample. So this is what we have. So what we actually measure, okay, till now what we saw DC, uh, was a DC source. What we can have is now alternating currents. And when once we have an alternating current, what we will have is a frequency associated with the alternating currents. And the properties or the response of this sample, such as the conductivity and other properties, they can be a function of the frequency. So what we call this property, it is impedance, which is the resistance to the flow of current. In a resistor, if you plot what is the current and voltage as a function of time, you will see that whenever the current is increasing, the voltage is increasing, and whenever it is decreasing, it is decreasing. Basically, they are in phase.
So
And for
basically,
just a resistive circuit,
sir, one general question. So
yeah,
impedance is generally for AC circuit and the resistance is for DC circuit, right? Or
impedance is for
impedance is generally for AC circuit and the resistance is generally for DC, right?
uh,
That's how we.
yeah, that's how we do. But impedance is a more general term. Uh, Even if you have a resistive circuit, there would be components which behave like a capacitor when we put uh, some AC, uh, some alternating current. And DC, you can
Okay.
consider it as a very particular case of an AC signal in which the frequency goes to zero.
Okay.
Yeah, so we will see later in the expression as well how we can look it in those terms. So yeah, this is for a resistor. It is just the impedance is the resistance. Now, when you come to a capacitor, for a capacitor, the impedance is given by uh, minus iota over omega c. So you see, omega is the frequency term and c is the capacitance term. So what is a capacitor? It is just two metallic plates placed very close to each other. Now you can imagine if you imagine its mechanism. Uh, Suppose you are sending an alternating current. For the first half of the cycle, let's say this part is positive and this is negative. And let's say this stays for around 2 seconds. And in the next cycle, what will happen? It will become negatively charged and this will be positively charged. So there will be alternating fields here, and uh, uh, these currents can be, there will be some external circuitry. So these currents can go in and uh, it can oscillate this way, which is why it is oscillating circuit. But now imagine if this omega goes to infinity, sorry, omega goes to, if omega goes to zero, z will go to,
Infinity.
Z will go to
Infinity.
infinity. That means, uh, suppose you are now using a DC source, the current will not pass through it because resistance here is infinity. So which should be true because there is no connection between this. So this is how, I mean, you can intuitively imagine. So this is a resistance to the flow of AC signal, and DC is a very special case in which omega goes to zero.
So uh, omega is basically our frequency, right? Oscillating frequency,
Frequency,
right?
yeah.
Oscillating frequency. So in DC we don't have oscillation.
In DC you don't have oscillation.
Yeah, that's the reason why we don't have impedance there,
Yeah.
or infinite impedance. You have to call it infinite impedance instead of zero impedance, right?
Uh, uh, the impedance will be infinity because omega will go to zero.
Okay. Okay.
Yeah.
But impedance and the resistance are not directly related in this case.
They will not be the same
Okay.
in this case. Resistance is not here. Resistance we use particularly for this case where the current is in phase with the voltage.
Okay.
Here you see the current is
That leading
leading
by
by,
90 degrees.
so this red plot is that of current, and this current you see it is shifted towards right side by 90 degree. Okay, and so this is what happens in a capacitor. You can remember it as a capacitor. It starts with C, so current has to lead. So current leads voltage by 90 degree in a capacitor.
Okay.
There is another component inductor in which the current lags by 90 degree. So this current has to come backward in time to so that it will match. So the basic components are this one resistor, capacitor, and inductor. These are the passive components of an electronic circuit. And in an inductor is nothing but it's just a coil of wire. So when you suddenly try to change the current, it will stop the change of current. Why? Because
Okay.
uh, as the current will pass through this coil, there will be magnetic field flux induced in this coil, and that is what is resisted by. Uh, that is there is a resistance to this change of magnetic field in a current carrying oil, current carrying coil. So this is called Lenz's law.
Yeah.
Yeah. So because of this, at uh, very high frequency, so very high frequency means a very fast change of the current, and hence very fast change of the magnetic field. And if that happens, this thing will behave as a, so you see omega will go to infinity, that means z will go to infinity, which is it will not allow current to pass through it.
Yes.
And at very low current, uh, sorry, at very low frequency, the change of current is really very slow. So the resistance to this flowing current is also low. So at that point of time, uh, in that case, it will behave as just a simple wire. So the resistance will go to, or the impedance will go to zero. I hope this is intuitively clear. This current and
Yeah.
inductor.
So L is the length, right?
No, L is the inductance.
Oh, inductance. Okay. Here it is
Yeah,
inductance. Okay.
yeah,
So
you,
Z is inductance and L is inductance. Okay.
yeah, L is inductance.
So Z is impedance and resistance, and okay, got it. Okay.
Yeah. So you might have heard of this RC circuits or LC circuits or
Yes.
RLC circuits. Like if not, then you will come across this in any electronics course. So these are the basic passive components. And how do we measure this AC conductivity? So in a particular situation, for example, a battery connected with a some circuit, you can measure any real component in terms of this R, L, and C. A battery will have some. So here is one particular model where the ionic conductivity will be given by this R naught, and the electrolyte conductivity can be modeled as this parallel connection between R1 and C1. And if you find the impedance of this circuit, so the way we find impedance circuit is, it is very simple. So you have to consider. I hope you know how to get the equivalent resistances like in parallel and series connection.
Yes, I've done it some time back. I have to recall it. Yeah.
Yeah, yeah. So okay, I'll just go through it again. Then. So, what is this? This impedance? Impedance is actually a complex number. What this I means? This iota means that uh, uh, it is the phase difference between the current and the voltage. If you write it in terms of e to the power I, so I, this theta is the phase. This is the phase lag between the current and the voltage. So since capacitor and inductor are these are they lag from the voltage by 90 degree, so they will come uh, in this imaginary axis of this Argand plane. And when you try to plot the impedance, it will be point in this complex plane. Now when you try to solve for this circuit, okay, just for you to recall, in series connection, if you have two elements, so this is element 1 and element 2, and it has some impedance Z1 and Z2, then the equivalent impedance is Z1 plus Z2. And in parallel connection, if you try to solve it, if this is impedance Z1, if this is impedance Z2, then the equivalent impedance will be given by the reciprocal of this 1 by Z is equal to 1 by Z1 plus 1 by Z2. And if there are two components like this, you can just remember it as product divided by the sum. Okay. So this is a very handy formula. Whenever you have any circuit, for example, how do we solve this circuit? That I will just uh, solve it here. For example, to solve this circuit, what you will do? So this you can consider as an element. So this you can consider as an element, and this you can consider as an element. Okay. Now these two are in series. The impedance of this is just R naught. So if you look at this expression, this is what I have written. Sorry, this is that expression. So R naught plus the second term. Second term will come from this particular element. Now these are in parallel. So the equivalent impedance will be product divided by the sum. The product is R times minus iota by omega c. So this is R1. R1 times minus iota by omega c1 and R1 minus iota omega c1. You got this how it happened, right? Did you understand this part? Or
Okay. Yeah, this is the resistance equivalent, right? So we get the R0. So typically, what you have done is using the Z real equivalent of Z real is equivalent of R equivalent is nothing but R0 plus. Okay, you're using the same formula, which is like in the impedance that you have used, or you are using a different formula.
no, no, I have used the same. Okay, maybe I will do this again. Yeah, here I have done it in detail. So you can think of this circuit as two elements. This is element 1, this is element 2.
Okay.
Now we know that these two are in series. So
Yes.
if we have two elements like this, Z1 and Z2, the equivalent will be Z equals Z1 plus Z2. For this particular case, Z1 is R0, which is this term,
Yes.
and Z2 is corresponding to this circuit. Now we have to see
Plus.
what this circuit is. This circuit is a parallel combination of R1 and C1. So for a parallel circuit, let's say Z3 and Z4 are in parallel. So equivalent will be Z3 Z4 divided by Z3 plus Z4. We have Z3 is equal to R1 and Z4 is equal to minus iota over omega C.
Yes.
Got it right?
Yes.
Yeah. Now you just substitute this and you will get this expression. And on simplification, what you will get is you will get a real term and an imaginary term. Both as a function of frequency.
Yeah.
Okay. Now at very low frequency, what will happen? So okay, this is the final expression here.
Yes.
Okay.
At low frequency, it's going to be almost negligible, right? So
Low frequencies, what will happen? At low frequency, this term will be 0. So the
yes.
denominator is just 1.
Yeah.
The real part will be R0 plus R1.
Yes.
Okay. And the imaginary part, since at very low frequency, omega will go to 0, there will be no imaginary part. Right?
Okay. Yeah. There's no imaginary part. Yeah.
Yeah. So at very low frequency, the impedance is just R0 plus R1.
Okay.
Right? So this point corresponds to the very low frequency. But the real part, where the impedance is only the real part, imaginary part is almost 0.
Okay.
Now, if you start
So
plotting, increasing the frequency, then what will happen? You see, the real part starts decreasing because it is frequency is now is in the denominator. So this will start decreasing. This part will start increasing. So increasing in the sense because it is minus z I am plotting. Okay. So basically, this is the curve that we will get. But what will happen at very high frequency? Very high frequency, you see, it will be denominator is so high, and the
yeah.
real part will be just R0.
Yes.
And here, omega square term will dominate. That when the denominator will start dominating, this term will go to 0. So here, this
Yes.
point will be R0. So if you plot this on a complex plane, it will come out as a semicircle like this. I hope you understand that point.
Yeah. It is going to be the positive side, like in the top,
Yeah.
because R is, yeah, R0 is 0, and it starts to go to the middle, which is real part, and then it takes to the R0 plus R1, which is uh, real and imaginary part together.
So once you go through this calculation, you will and analyze this for a while. You will understand that this will be the plot. Okay, so the point here is to note that you can model a real system in terms of this equivalent circuit. So another, so this is a more when you take into account some further processes. For example, there would be some charge transfer in the electrolyte or mass
Yeah.
transfer in the electrolyte. For them, for those processes, you can model them as these equivalent circuits. So given a physical system, you can have an equivalent circuit, and this is an example of some of the other materials. So here, if you plot for this particular circuit, so the mass transfer earlier we had only these two components, right? Now we have the three components. So
Three
this will
components. Yes.
correspond to R naught, and this semicircle will correspond to the charge transfer. This will correspond to the mass transfer. So from simple impedance measurement, you can tell about this physical phenomena happening in the electrolyte. So the point here was to uh, uh, the point was to show that a real physical system can be modeled as these equivalent elements, circuit elements.
In the previous slide, we are x and y axis was same, right, or different?
X and Y axis are same. No,
The
no.
previous slide. The previous slide. The previous slide. Yes. Okay, it's Z real, but
See,
what is
this
the
X axis is the real part of Z, and
yes?
Y axis is minus Z imaginary, which means here what is getting plotted? R1 square C1 omega divided by omega square R1 square C1 square plus 1. That is the function which is getting plotted along this.
Okay.
Yeah. Similarly,
So you
one
can
can calculate for this what is the equivalent circuit, and when you plot as a function of omega, then you will get this plot. For low frequency, it is here, and as the frequency increases, it will come here like this till here. So
yes.
that is it. Now, the next lecture is about the electron gas. So here, in this the gist of this lecture is that the electrons in a solid, they are treated as a gas. So till what is the justification that we can consider electron as a gas? For that, the professor gives two justifications and one caution as well. So let me first tell the model. What is the model that is being used? A solid will consist of these ionic cores, which are shown here in this blue dots, and every atom. Uh, so an atom will have lot of quite a number of valence electrons, and one of the outermost electron to which it is loosely bounded, that will be given out. So the valence electrons, each of these atoms will give out a valence electron, and once those valence electrons are given out, it belongs to no particular atom. It is free to move around in this volume of these atoms. These atoms will form a solid boundary. In this boundary, these electrons are moving. So, what is the justification? Uh, so, the approach is to we know what is an ideal gas, and we will use what are the rules we know of this ideal gas and impose it on this electron gas. And the gist is that metal behave as if they have free electron gas inside them. So how do we justify this analogy? So in a solid, there is a lot of empty space. So in a simple cubic structure, there would be some packing fraction around 50% of the void. And in face-centered cubic, if you calculate, it would come out to be 75% is the packing fraction. Around 25% void will be there. So what we have is a lot of gaps, and in those gaps, the electrons can move through. Similarly, the gas that we have in our atmosphere, they can move through the empty spaces. The space is actually empty and it is moving around. But we have to be cautious. Why? Because if you look at the number density of gas molecules, it will come out to be around 10 to the power 25 molecules per meter cube. Whereas, for example, if we take silver, then the number density of electrons is around 10 to the power 28 electrons per meter cube. Okay, so there is a difference of three orders of magnitude. So that is why we need to be careful on where we can go wrong if in case the model doesn't work out. So, so these are the basic assumptions. The assumption is that the electrons undergo collision with each other, and these collisions are instantaneous. And once the collision will occur, uh, electrons will lose the memory of its uh, velocity, what was the velocity it collided with, and then it will go ahead with some other velocity. So of course, the conservation of momentum and energy would be satisfied. So the Coulombic interaction between these electrons are neglected. But we are saying that these electrons are behaving as an ideal gas particle and they are colliding. The second assumption is the between these collisions, there is no interaction of these electrons with the ionic core or uh, with the ionic core. So what we'll be doing is an average resistive term will be introduced to account for this interaction. Okay, and the third is the mean free time for the collisions that will be denoted as this tau. This is the average time between the collisions, and these electrons will attain equilibrium with the surroundings using these collisions with the other electrons. And the repulsive term between electrons and attractive terms with the answer neglected. And what we want to predict based on these assumptions is that electrical and thermal conductivity. So, what we saw was we have a method to measure the AC and DC conductivity. Now we are making a model based on certain assumptions. What we will do is from this model we will predict this electrical and thermal conductivity and compare it with some experimental results. And how those experimental results were obtained, that we just studied in the uh, 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 first lecture of the last week. Okay, now we will look at the ideal gas and how we compare this ideal gas with those of this electron gas. So this particular portion is called the kinetic theory. In kinetic theory, the gas is considered as randomly moving atoms or molecules. And if you go through this calculation and just show you the key result is that So pressure. So this is one which we have from the. This is the gas law. PV is equal to nRT. From the kinetic theory, if you go through this calculation, you will get PV is equal to m. This is the mass of the gas molecule. N is the number of moles of the gas. Na is the Avogadro number, and this V square is the average square velocity. So this will come from average kinetic energy of the molecules. Okay, and divided by 3. So this term 3 comes from this derivation. If you go through this, you'll get it. And once you compare these two equations, you will get RT is equal to m Na V square average by 3. And if you arrange that expression, you will get this uh, this expression in this box. What it means is that the average kinetic energy of a molecule, and this kinetic energy, what is the translational kinetic energy? Okay, it is not the rotational or vibrational kinetic energy. It is the translational kinetic energy, and it is 3 by 2 times kBt, or what you can think of it as 3 times half kBt. So there is this law of equipartition of energy. So the number of degrees of freedom are there in the molecules. Those uh, that will get multiplied with half kBt. So for example, in a gas molecule in a box, there are 3 degrees of freedom: translation along x, translation along y, and translation along z. These are the 3 degrees of freedom, and each degree of freedom will get half kBt contribution. So, okay, this is just this we get from the kinetic theory. From this, what we can get is okay. So this is the total translational kinetic energy per molecule. Now, if you have, let's say, anti molecules are there per unit volume. So the kinetic energy of the molecules will be anti molecules times what is the average energy per unit molecule, which is 3 by 2 kBt. And so since this is the energy, you can now calculate what is the specific heat. Specific heat is the derivative of energy with respect to temperature. And if you do that, it is just a linear in T. This CV will be just 3 by 2 and kb. Okay, now the point to understand here is that how do we extrapolate it to the electrons? In electron, so in ideal gas, we had this mass term, right? We had this mass.
NT
Mass
here
just
means translational, right? N number of moles translational, or NT, what is that?
this one.
Yeah, it's
NT is
molecules.
just a number. So a number, this three refers to temperature.
Okay.
Okay. If there are NT molecules per unit volume at temperature T. Okay. So yeah. So what we have, this expression we have for the ideal gas. Now we want to extrapolate it to the electrons. Earlier, this m was the mass of the gas molecule. Once we extrapolate it to the electrons, this m will be the mass of the electron. So this is the first consideration. Now, when we consider a solid, when you consider a gas, it is just the gas and there is no other species in it. But once we consider a solid or a metal, there would be this ionic cores as well as these electrons. So the specific heat that we will get when we extrapolate this kinetic theory is the specific heat of electrons in the solid. So there can be the specific heat coming from other species, like for example the ionic specific heat would be there. Okay, so we are not considering that term. Here it will just be the electronic specific heat. This is the only point we have to take care here. Okay, so that's all there in the theory. We can have a discussion of some of the question answer of last year.
Yeah.
Okay, so what do you think the first question will be?
Lithium-ion batteries, the charge carriers are electrons as well as ions. Lithium-ion. Lithium has a yes, true.
This is uh, true, right?
Yes. Yes. I don't know whether I'm not audible.
Just
It's true. Resistivity is an extensive property. True.
just a second. I think it is in lithium-ion batteries, charge carriers are electrons as well as ions. Yeah, true. Because it will be yeah. Because both of them will be conducting. Electronic conductivity will be less, but non-zero. Yeah, so this is true. What about
It's an
this?
extensive. Yeah, true.
It is resistivity. R is equal to rho L by A.
Yeah. Yeah.
So, extensive property means the property which depends on the dimension of material.
Yes.
So, is resistivity a extensive property? So, for example, if I have a silver, silver of let's say 10 centimeter, 5 centimeter, and another silver of this is 15 centimeter, 2 centimeter here. The resistivity of these two will be same or different.
Resistivity of silver with a different dimension. Resistivity constant, right? In this case, for silver.
Yeah, resistivity will be the same. It is independent of the dimension.
So it's not an extensive property. Okay.
It is
Yeah.
not an extensive property.
Okay.
So
The
this
resistance is
statement is
extensive, is it?
false.
The resistance is extensive, correct?
Resistance is extensive
Okay.
and resistivity is intensive.
Okay.
Okay, what about this? For a resistor, what is the
False.
impedance?
False. It is not always true, right? Or is it true?
It is for a
Because
resistor.
only for resistor. Yes, true.
So this is true. Yeah. Okay, what about this? A capacitor. A capacitor displays very low impedance. So the formula you have to remember is this.
Minus I by WC. Yes. Low impedance in response, low frequency. When the low frequency, it will be infinity, right?
Yeah. So when the frequency is low, C will go to infinity.
Infinity.
Sorry,
Z. Z.
that is infinity. So high impedance. So this
Yes.
statement is false.
Yes.
Okay, so what about this? In a simple cubic structure, larger atoms result in smaller fraction of vacant space.
That's true, right? Because atoms are big, and it accommodates itself within the available space. Because
No,
we have
what you have to think of it as in a simple cubic structure, the vacant space is around 50%. Yeah. Why? Because even if the atoms are larger, they will they will be usually identical. And when it comes to the fraction, okay, so fraction means uh, like maybe we can go through the calculation once. If you see here, yeah,
this one, yeah,
yeah. So
very good.
irrespective of the size, so for a small size, it will be just like this, given that they are in simple cubic. And for a large atom, it will be like this. So R and the lattice constant will be A, and R is equal to A by 2. Whatever be the size of this, when we say that they are in simple cubic, the packing fraction is independent of the dimension of the size, because this R and A will cancel out. You got it right? It is a fraction.
Yeah,
So even if there is larger atoms, the fraction of the vacant space is around this 50%. And to be precise, it is
two. It's 48% actually.
yeah, it will be this pi by 6, 48. Yeah,
3.14. Yeah,
yeah, around that. So this statement will be false.
false.
Okay, now this uh, both ionic and electronic conductivity can be accurately measured using two probe method.
No, false.
False. Why?
Because we'll have a loss. Um,
Yeah, correct. We'll have a loss here. Then yeah, this is correct. Okay. In a four probe measurement, the resistance of an ideal voltmeter, which is connected in parallel with the sample, what will
zero.
this be?
Zero.
No, you have to. It is the resistance you are asking. I'll just draw the circuit again.
It's in parallel with the ideal voltmeter.
It is an ideal voltmeter. Okay.
Yeah. Only if the resistance is zero, it can pass through, right? Otherwise,
Just a minute. Okay. Now, what do we want? So this is giving some current, current,
yes.
current, current. Let's say this has a certain resistance. This is a resistive uh, circuit. Okay. And the current is I. So what is the potential drop? Ideally, it should be when it is not connected to any voltage, any voltmeter. The potential drop would be
No, no potential drop, zero.
no. It is
IR.
connected to the source, but
It's related to the current.
not to the voltmeter. The
Okay.
potential drop would be I times R, current times resistance, is the potential drop across the resistor, right?
Yes.
Yeah. Now imagine that this will have a resistance, let's say R1. Okay. Now what would be the equivalent resistance here?
It's parallel, so it will be 1 by R1 plus 1 by R.
1 by R1 plus. Yeah, I mean, okay, one. So basically, you have to remember this R1, R plus R1.
By R.
Okay. So the now, or another way to look at it is like, since it has some resistance, it will take in some current I1, and let's say the current through this will be IR. Okay. And I will be is equal to I plus I1 plus IR. So this current is getting divided into IR and I1. Now the problem here is the potential drop across this is I1 R1, and here it is IR times R. So I1 R1 equal to IR R, and these are connected by this equation. So now see, this IR is less than I. You
Yes.
got this point?
Yes.
So the potential drop that this guy will measure, yes, so this is what it will measure. I1 times R1, right?
Yeah.
And this IR times R, IR is less than IR times R is less than I times R. So we wanted to measure uh, this value of the voltage. But what we will be
Yeah.
reading is a value which is lesser. Got it right?
Yes. So it
Now
is less small negative value
a
or
small value we will get, not negative.
okay.
Okay. Now how do we rectify this problem? So in case this IR, so IR we want to be very close to I. So this I1
Yeah.
has to be very, very small.
Yes.
Okay. So how do we make this I1 very, very small? If I1 is small, this R1 we need to choose such that R1 is high.
High. Yeah. High
And
resistance.
once R1 is high enough and I1 is small enough, then this IR is almost same as I. And then this value will be very close to each other. So what we need is R1 to be as high as possible. And R1 is the
Yeah.
resistance of the voltmeter. Got it right?
Yes.
So what we want R1 to be
High.
high.
In, okay.
Okay, so what would be the correct answer now?
Infinite. Okay.
Infinite. Yeah, correct. Like I hope you understand why it is so.
Yes.
Yeah.
Yes. Yeah. It is better. You explained it very well.
Yeah. Okay. Okay. Now we go to the next question.
Free
Uh,
electron gas of a metal
Free electron gas
solid.
of a metal
consists of valence electrons released by each atom which roam inside the solid. Electrons that have escaped the solid. It's only the valence electron.
Yeah,
That's the right one.
yeah, correct. Why is this not a correct answer?
All electrons will, because the other shells which are inside the orbitals will not be free.
Yeah. So, and electrons that have escaped the solid and are in vector phase outside. Yep. And they has to be they have to be inside the solid
Yeah, there
boundary.
is no.
And electrons belonging to gases. So there are no gas
It will
inside
not.
the matter. Okay. Now the motherboard of your computer conducts electricity to all the components. What are the conducting spaces? So a motherboard will consist of
Semiconductors and
semiconductors, some
it will be electrons, ions, and holes. No protons.
ions, holes, and there would be some backup battery kind of thing,
Yeah, ionic conductivity.
and ions also answer. Why not protons?
Protonic conductivity is not part of electronics, right?
Yeah, protons are just it are these are in the nucleus, and they will be
Nucleus.
in the atomic core, so they will not conduct. Okay. In the common AC impedance equivalent circuits, elements where there is a phase difference between current and voltage.
AC impedance, right? In the impedance, it is yeah, impedance equivalent circuit. That is actually we have two, both inductance and capacitance. We have
Yeah, correct. Because for this is for a capacitance, so there is a phase
yeah,
difference of 90-degree, and the way we have
is
to remember is current
is ahead by 90 degrees,
current is ahead
by
by
90
90
degrees of
and
the
in
voltage.
inductor
IWL.
right L and this is R. Okay, so here there is a phase difference of 90-degree. Okay, so now what will be the approximate packing fraction of an element having atomic number 84 is the most common form? Okay, so element having atomic number 84 is polonium,
Okay.
and its most common form is alpha polonium. Okay, and alpha polonium, if you just Google it, you will find it that it is in simple cubic form. So there are actually two forms: alpha polonium and beta polonium.
Yeah.
Alpha polonium is in simple cubic structure, and beta polonium is in rhombic form, or it is called rhombohedral.
Or above it.
So it is just uh, like you know what a rhombus is, right?
Yes.
So it is just a cube in which the two planes are not on top of each other. It is just, I mean, there is this angle is not 90-degree. That is the beta polonium. But the most common form is simple cubic. And what is the packing friction of
48% or 50%.
48%? Here it would be. Uh, so what you have to take here is 50%. Yeah. Yeah. So the point here is, irrespective of what the material is, it is alpha polonium or some other material which is in simple cubic form, as long as it is a simple cubic, the packing fraction is just this 48% or this 50%. That is irrespective of the size of the atom. Okay. To calculate the total number of atoms per meter cube for the highest electrical conducting material, this metal is silver. Okay. And silver is a face centered cubic crystal structure. So how do we calculate given the information that silver is in face centered cubic? So another important data is you have to
Is
so
4r equal to root 2 by a, correct? Or r equal to root 2 by 4a.
yeah, but how do we get number of atoms per meter cube? For that, the information that you need is one is this cubic crystal structure, another is this lattice constant. So
Yes,
you know that let's
a
say
is
imagine that this are touching each other. Now for silver, you need to know what is the lattice constant. So and the lattice constant it turns out to be around 0.408 nanometer. Okay. Now in a cube of volume, let's say this is L. In a cube of volume L cube, how many atoms should be there?
um, 3, it's basically 3 by 4 pi r cube, right?
No, what I'm asking is how many
4 by 3
atoms would be there in one
in a,
cubic volume if it is an abscissa?
let's say it's going to be 1, 2, 3, 4, 6,
So I'll tell you what how you should calculate this. So in a
1,
face-centered cubic, you will have at all these corners
yeah,
one
8,
atoms.
yes,
Okay, and there would be eight of these atoms,
face
and
plus
each of
8,
these eight is contributing a volume of 1 by 8 of the sphere, right?
yeah,
Why? Because this particular sphere is shared by 8 cubes. If you stack these
yes,
cubes adjacently, this will be shared by 8 cubes. Got it right?
yes, yeah,
So 8 times 1 by 8 of the volume of this sphere.
4 by 3 pi r cube,
Okay, this is the corner atoms. Now, what about
yes,
the face centered atoms? There are six faces,
yes, 6 faces,
six faces, and each of these is shared by two cubes,
2
right?
cubes, yes. So 1
So
by
it
2,
is
1 by 2, 4
giving
by 3 pi
one
r
by
cube,
two of the volume. Okay, so so if you simplify, what you get? This eight will cancel eight. This will become three. So 3 plus 1, it is 4 into 4 by 3 pi r cube. So it is 4 spheres. Got it right? So in a cube
yes,
of volume L cube, there are 4 spheres.
yeah,
This point is clear?
yes, clear.
So
four spheres
4
total. In the,
atoms of silver per volume of L cube is the number density.
yeah,
Okay, 4 atoms. So now it is 4 atoms divided by what is L? L is this one
408
0.408
whole cube.
nanometer. We want in meter
Yeah,
cube.
minus,
So
yeah, 10 power minus
into 10 to the power minus 9
whole cube.
meter whole cube, right? So
Yeah,
what we will get 4 divided by 0.408 cube into 1 by 10 to the power minus 27 atoms per meter cube. Okay. So now if you solve this,
4. Yes.
this will turn out to be
1.2. 4 into point 4 is 0.1. 4. It's like 0.6 to the 4 by 0.6. This one.
yeah, it comes out to be 58 or 60.
Or 6.25
How much it came
into
out?
10 power. 6.25 into 10 power 27 is like approximately.
6 point
0.25 into 10 power 27. Yeah.
10 to the power 27. This is what you're getting, right?
Let me tell you one more time. Just
Yeah,
zero
yeah.
point
Okay.
0.4.
This is about
0.
the. So this 6.2 you can consider is approximately as 10. So the correct answer would be around 10 to the power 28.
62.5 into 10 power 27, which will be, yeah, 27 means
62.
6 point, yeah, 62.5 into 10 power 27.
So this turns out to be, let it here, n equal to 6 into 10 to the power 28 per meter cube. Okay. Now your correct answer would be around. So this would be the correct answer. And if you remember, we had calculated the number density of electrons. That also turned out to be around 6 into 10 to the power 28 electrons per meter cube, where we had taken
Yes,
the valency 1. So each atom is contributing 1 electron.
for silver, yeah.
Yeah, so it is in very good match. And here we didn't consider uh, any lattice structure. We just took, we just measured what is the density, what is the atomic mass, calculated the number of moles, and then we calculated. Here we obtained it from this lattice considerations, and it is matching very well. Okay, so now we go to the next question. While using AC impedance, charge transfer and mass transfer resistance are okay. You, I hope you remember the equivalent circuit for this was this R naught,
Two arches.
R1 C1, R2 C2, and the response was like This is minus Z imaginary and Z. And how we obtained this plot? At this was at low frequency. As we increase the frequency, so like this. Okay. Now, what would be the correct answers?
Actually, series and plus mass transfer is dominant at low frequencies than charge transfer.
So what is this? This is actually an model of an electrolyte.
Yes.
Electrolyte, or like you can the power source. It is usually in parallel. Since it is a power source, it will be in parallel with the other element. So whatever the other elements there, that would be in parallel. Okay,
In
now
parallel.
what about this? So if you remember the plot, this was the mass transfer
Yes.
and this was due to charge transfer. So what would be, is this correct or uh, correct or wrong?
Yeah, mass transfer is dominant at lower frequencies. Correct, right?
Yeah, this is correct.
Yeah.
Here, majority of this is due to the mass transfer. The
Yes.
dominant part is the mass transfer. Okay.
Measured by varying the frequency values also is correct.
Yeah, this is correct. Because we are actually varying the frequency and obtaining this. So these three are your correct. Okay. What will be the average translational kinetic energy for gold metal at 0 Kelvin?
And this one is translation energy. We saw mv square of mv square is equal to T by 2 kV and T by 2 kVt. It is
Yeah,
nothing but 0 Kelvin is T is 0, then it is 0.
you're correct. Okay, there is another. This is question number 8. One question I missed. So the question is EEV is the. And your options are. Okay, what about this?
Free electron contribution in the solid is correct, for example.
Yeah,
because we have 3 by 2 NTKB, your formula.
yeah. It is only the free electron contribution, and the ion cores are actually static. So this is from the free electron model. So this specific heat is not the specific heat that you will measure when you do the experiment. It will just be a term which is getting contributed because of these electrons. Okay, so that is
When
all.
it comes to this inert gas calculation, when
Inert
we are
gas.
saying, inert gas interaction, for example, at different pressures, what is the formula we should use or what is the approach we should follow?
What you is this you're asking about this?
No, in the inert gas,
Yeah,
interaction between atoms at different pressures, PV is equal to nRT, right?
yeah.
And
Okay, okay. So there is one uh, for
this is ideal gas, PV is equal to nRT.
so this is for ideal gas. Yeah.
Yeah.
So
For inert,
uh, inert gas are usually ideal gas, right? When at certain um, conditions.
yes,
But at this gas law, this will fail when we go to high pressure. When you go to higher pressures, that is because there will be some interactions coming in, and
yeah,
here and when the pressure is high, and maybe the temperature is high,
yeah.
or at low temperatures, what will happen is this pressure will decrease because there would be some attraction between the uh, individual atoms. So this pressure will decrease, but it will decrease something like this, and the volume will be also decreased because now this molecules itself. Earlier we used to neglect the volume of the molecules. Now the volume of the molecules will be also considered. So there is this formula called van der Waals.
Is it van der Waals interaction or
Uh, van der Waals is a very particular a very particular kind of interaction. Right. So van der Waals interaction is, suppose you have a gas molecule, and let's say these are argon. Why argon? Because it is an inert gas.
yeah,
What will happen is usually when there is no other interaction, the ionic core is at the center of this electron cloud.
yeah,
But in a gas, there will be a slight displacement of this ionic core and the electron cloud. So this will act as a dipole. And this dipole is actually a fluctuating dipole. So sometimes the dipole moment is this, sometimes dipole moment is zero, sometimes dipole moment is like this. So when you look at an argon gas, it is a mixture of these varying dipoles. And the interaction between these dipoles, it goes as minus 1 over r to the power 6. Okay, this interaction is called this van der Waals interaction. And the gas law gets modified, and the gas law, it is given as this. So you can search for this van der Waals gas equation. But yeah, this we don't have to know for the particular purpose of the syllabus. Earlier it is PV is equal to RT. Now it is this. Yeah, that's all. But this part is not in your syllabus. All the important part is to understand that how we can apply the gas law to the electrons
Yeah, in the atoms, when the interaction will be high with the high pressure,
in atoms.
inert gas with high pressure, there will be high interaction of the
There will
atoms.
be high interaction. Yeah. So
And
so
yes, sorry.
and
Yeah, so if it is high interaction, that means the volume also will be coming down.
yeah, because earlier we are neglecting the volume of this individual gas molecules. At high pressure, we have to consider what is the volume of this gas molecules. That is why we have to the available volume for the gas is reduced. So we need to reduce that reduce by this term P minus NB, and the pressure. So to correct for the lowering of pressure, we have to add a term. There will be some attraction between this individual gas molecules. To correct for that, we have to add a term.
Okay.
Yeah. So, but this interaction is not the same as electron-electron interaction. Electrons, they uh, they do Coulombic repulsion, which is actually neglected. So these complications we are neglecting. In very simple terms, we are considering ideal gas. Ideal gas means just this thing is getting followed. PV is equal to nRT. Based on this, we are saying that okay, let us apply this to the electrons and let's see what will happen. And this why? Because we have a kinetic theory, and kinetic theory was actually very successful during the times when the free electron theory was proposed. Uh, the free electron theory was proposed during 1900s something, and it was very recently this idea of kinetic theory was there. Earlier, people used to think that the gas is a continuous flow of matter. There was no concept of an individual atom. Okay, and when this atomic theory came up, that okay, gas is nothing but a collection of small particles, small molecules. It was a very big breakthrough in those times. So, uh, and like you might have heard this also that uh, Feynman in an interview he told that if you want to transfer only most of the knowledge in only one sentence, what would that sentence would be? Then he had told that uh, the fact that the atomic theory, the fact that things are made up of atoms. So in those times, it was a very big thing.
And one more question on the FCC and BCC. So FCC has this thing, right? Closely packed structure, right?
Yeah,
Compared to the BCC.
yeah, true.
And does it contribute to having more free space? How do you calculate the free space?
Free space. Okay, you have to actually calculate. Okay, I will just tell you how we calculate the free space. For example, if you have an FCC, okay, this is a cube. Now you imagine closely packed FCC lattice. So I am drawing like this, but imagine that these are okay. These are nicely arranged. Okay, now if you say that the lattice constant is A and the radius of this sphere is R, Now see along this line. Along this line, what is the length of this blue line?
2A.
No, this is A, right? This is A,
Root A. Root A, right? Root 2A.
root 2A. Okay, and in terms of the radius of the sphere,
R is equal to 3 root 2 by 4A.
yeah, I mean this root 2A is equal to 4R, or R is equal
Yes.
to root 2
Root
by 4A. Now, how many spheres in a volume of A cube? How many spheres are there?
In a
So
cube,
it
we have
is. You
8.
remember that calculation with the grid now? 8
Yes,
into 1
8.
by 5,
8.
1 by 8, 4 by 3
4,
by R cube
6
plus
into 1, 2.
uh, 6
6
spaces,
into 1 by
half
into
by 3
4 by
cube, which is 4 into 4 by 3 by R cube. You got it?
here.
Now, volume of the cube occupied by the spheres is 4 into 4 by 3 by R cube divided by volume of the cube. This is the packing fraction. Definition
Yes.
of packing fraction. This is A cube, right?
Yes.
Now what we have is 16 pi by 3 R by A is R by A is root 2 by 4. So root 2 by 4 whole cube. To calculate this will come around 75%.
Yes. About BCC,
About BCC, okay.
if I
In BCC, what you have to consider, it is body-centered cubic.
yes.
If you have a square like this, sorry, a cubic lattice like this, on each diagonal you have a sphere, and
Yes.
1, 2, 3, 4, 5, 6, 8, and on center you have one.
Yes.
Yeah. And if you connect this diagonal from this diagonal to this diagonal, okay, what is the length of this diagonal? If this is A,
Mm, it's A.
okay, so
Uh,
to make it easy for you, you imagine this line also. Okay, this is on this face. So if this is A, this is root 2A,
A. Yes, 2A.
this is root 2A, and this
Yes.
is A. So now this will be,
That will be the diagonal root 2A plus A the whole square. Which is,
yeah,
root A square plus so 3A square.
3A square root of that.
Square root of
So root 3A will be is equal to 4 times the radius, 1
yes.
r, second r, third r, fourth r. Got it right? By this,
Yes.
this is clear, right?
Yeah. So now it is R by A. Yeah. So now the packing factor for this is based on, again, same formula we have to follow, right?
Yeah.
4 in
Now you just
not
do the same analysis. Number of spheres in a volume of a cube will be how much?
yeah,
Say one the edge, the one on the corners, they will
yeah,
be just 8
1 by
times
8.
1 by 8,
Yeah,
4 by
4
3
by
pi
3.
r
Yeah,
cube. Okay.
4 by 3 by r cube.
And the one in the body center is 4 by 3 pi r cube, which
It
is
is
nothing
2,
but
4,
2 times 4 by
2,
3 pi r
4 by
cube.
3,
Right?
8 by 3 by r cube.
Yeah. So now volume occupied by spheres. So packing fraction is volume occupied by spheres,
Divided by the total volume, a cube.
volume of cube. This will be 8 pi by 3 by a whole cube. Okay. And you just have to substitute 8 pi by 3 and root 3 by 4 cube. So 8 by 3. Yeah, this is your card value.
5 by 2 by 3.14. Wait, 1.732 divided by 8. That's the packing factor.
Got it right?
Yeah, 0.67 is the packing factor. 57%.
7. Yeah.
So
So
it's
you
true
calculate
that
the
the free space is more because of the packing factor.
what?
The free space in free internal space in FCC is more because of the packing factor.
Because of the packing fraction, yeah. So the free
Yeah.
space
But
is just 1 minus PF.
yes, 1 minus. So it has more free space, right? Then uh,
Cubic
BCC
will
has
have
more free
more free space. I mean, you can just see.
space. Yeah. Yes. 0.61 means it will have more space. 0.33, whereas there it is only 0.25.
Yeah.
Okay. Thank you so much, sir. Actually, it became a one-on-one interaction for me.
Yeah, it is actually good.
Thanks to this. Yeah, I'm learning.
Okay.
Thank you, sir. So it'll be the same time next week, right?
Same time next week, yeah. And I
Okay.
think this will this recorded uh, session as well as the uh, this PPT will be sent to you in a link.
Okay, sir.
Okay. Thank you so much.
Thank you,
End
sir.
the session.